Today, I'm going to be presenting problem number 14, ruler trick. Without further ado, let's get straight into the problem statement. The problem tells us that if we place a ruler on the edge of a table and throw a ball at its free end, the ruler will fall. However, if we can cover part of the ruler with a piece of paper and repeat the throw, then the ruler will remain on the table while the ball will bounce off it. What we have to do is explain this phenomenon as well as investigate the relevant parameters. But first, we will try to qualitatively explain the phenomenon. You see, when the ball hits the ruler, then part of the ruler on the table tries to lift and air tries to insert under the paper. Since the force is so sudden, air does not have time to enter under the paper and therefore some sort of vacuum is created. The atmospheric pressure force on the paper, which you can see with the green arrows, is great, and therefore the impact force from the ball is not able to lift the paper. Now that we have some sort of understanding of what is happening qualitatively, we can move on to the quantitative analysis of the phenomenon. We will decompose this analysis into separate steps, beginning with the free fall of the ball on the ruler from height h and no initial velocity. Then we have the collision of the ball and the ruler. The ball basically hits the ruler with a velocity of v1, which can be calculated. And then the ball bounces off of the ruler with a velocity of v2. The coefficient of restitution is e and can be calculated as it goes. The change in velocity during impact is delta v and can be calculated as following. So the impulse j is equal to the mass times delta v. Knowing the duration of collision, we can calculate the maximum impact force of the ball on the ruler. Now that we have established this first approach, we can establish a new one, a second way for us to approach the quantitative analysis of the problem, where we establish a natural frequency for the system of two bodies. The total impulse j will be 2 times F max over the angular velocity, and then the impact force will be F max. Combined, if we know F, we can calculate the impact force as following. The paper rests on the table and on the ruler. Upon a sharp strike on the free end of the stick, air cannot go under the paper quickly enough to compensate the atmospheric pressure on top, as we previously mentioned. Therefore, air cannot get under the paper, and therefore we have some sort of vacuum, as it was mentioned. Using this formula, we can calculate the minimum surface area of the paper for a given ball mass and initial height, and show the relationship between the independent parameters, which is mass and also surface area. Moving a bit further, we see that the problem statement suggests that the ball bounces off the ruler without breaking the ruler. We can use this model to calculate the maximum torque for the ruler not to break, which is the following. And something that I believe I have to mention here is that in our experiments, we ensure that the ruler will not break by using a steel ruler. So it's hard enough not to break. After all of this analysis, both qualitative and quantitative, I believe we can now mention some of the relevant parameters that we derived through our theoretical model, and which we will also investigate in our experiments. So basically, we will have ball mass and the table as independent parameters. We will have the paper size being a dependent one. And finally, we have the height of the toss, the ruler placement, and the ruler material being controlled parameters. Now, I believe we have to say a few things more about the independent parameters. We have the table and the ball mass as mentioned. So the first hypothesis regarding the table being the independent parameter, we believe that if we conduct the experiment on a table with holes, air will be able to get underneath the paper and the phenomenon will not proceed. And now regarding the ball mass, we believe that using the theoretical formula, we will be able to calculate the minimum surface area of the paper needed for each given mass. As the mass increases, the minimum surface area will also increase. Here you can see our experimental setup and more specifically the ball release mechanism we will be using. We have this free fall adapter and this metal ball here in our schematic. The reason we are using this is so that we can ensure that no initial velocity is placed upon the ball. Now, Regarding our apparatus, which is things other than our release mechanism, we have, of course, metal balls of different sizes. We have the steel ruler so that it doesn't break. We have the sheets of paper, ball release mechanism, table with holes, compact table, and finally a camera for our recording purposes. And here you can see a video of our first experiment. So here we have a table that has holes, and we see that if we conduct the experiment on a table that has holes, the phenomenon will not proceed because the air can get underneath the paper and therefore no vacuum is created. And therefore our hypothesis is confirmed. Now let's move on to our second experiment, for which we used Tracker, which is a video analysis and modeling tool. I believe you're all familiar with it, to measure the duration of collision and then calculate the theoretical value for minimum paper surface area. Here you can see a picture of us letting a ball fall from a height of 10 centimeters. Here you can see a table where we have the percent error between our theoretical and experimental values for the minimal surface. And you can see that for some of the calculations, it is somewhat acceptable, and in some others, like the ball mass of 5 grams and 2 grams and 1 gram, it's pretty unacceptable. Here you can see our velocity and height graphs. So these are for balls of 64 grams, 33, and 14 accordingly. And here you can see the graphs that were derived from Tracker. And here you can see a graph where in the y-axis we have the paper surface area, and in the x-axis we have the mass. And we have two lines, both theoretical and experimental one. And basically, yeah, I think that's it. That's all we need to say about this graph. And here we have the ball mass to minimum surface area of paper graph. So as you can see here, the minimum experimental value of the paper can't be less than approximately 45 kilometers squared, because it must cover the surface of the ruler. So basically, in our second experiment, our average error was 5.42%, which we mentioned before. And the theoretical model does not apply when the calculated area is smaller than the area of the ruler. That explains the big errors in those values, because as we can see in this previous slide, here you can see we have some really huge errors, like 61%. So if we exclude those, our average error is way more acceptable, which is 5% rather than 23%. Here we will be explaining some errors that might have occurred throughout our experimentations. So the first one is the accuracy of the duration of collision, which was obtained by Tracker, which is, I would say, reliable, but not fully, of course. Then we have the accuracy of the coefficient of restitution value, which was obtained by bibliography. And finally, we have the accuracy of theoretical velocity calculations. Now, our report is coming to an end, so we can see a summary of it. So to remind you a bit about what happened, we first explained the phenomenon qualitatively and then moved on to develop a quantitative theoretical model that predicts the relationship between the mass of the ball and the minimum surface area of the paper for a given height. And we had two different approaches for this. We talked about the parameters and hypotheses of the problem and explained the experimental setup that helped us reduce human errors. And finally, we analyzed the two experiments that were done and presented the data acquired. And finally, we talked about the possible errors of our experiment as seen here. Here are our references that you can see. And finally, I'd like to thank you, and I would like to also welcome the opposition for the clarifying questions. Thank you once again.